estudiantes de química. All right, so second practice problem, and then I have a third one, and then hopefully I can leave you alone for a little while. But the idea is that you can analyze any data from a lab-based situation, and you can do a titration or do a data analysis, volume analysis, whatever it may be. Ready? Almost. Pull out your piece of paper you're working on earlier. I want you guys to read this and try to write down the two reactants for the overall titration. It might take a second to figure out what's going on. If you're looking at lab stuff, hold off for a minute. I just need your attention for about 15 minutes, okay? So you had a tin ore, which that's just a rock with tin in it, so it's solid tin. They did what to it? Okay, well they masked it, yeah, and then they added acid. And that's simply just to extract the tin ions from the rock. That's what they did. So they made tin ions. What's the tin charge now? 2, okay? So basically what's happening before all this is tin is going to tin 2 plus 2 electrons. And this is before reaction, like before the truest reaction that we're concerned about, which is the titration. That's just to get the tin out of the tin ore. So then now it says the solution of what? So it's hydrochloric acid and tin. So I know that you're like, okay, HCl and tin 2 plus, but really that acid is just there to allow us to balance an acid. That acid is just there to say in acid. Okay, do not write HCl down, period. But you have tin 2 in solution, and I'll just put in acid over here so we remember that there is acid present. And what's the tin 2 in solution reacting with? Say again? Potassium permanganate, right? So we've got potassium permanganate as our other reactant, but we know that potassium is our spectator, it's going to be out, leaving us just truly with permanganate. So as you read all that, you understand that we're just pulling the tin out of the ore to make tin 2. The acid is just there to acidify the solution for balancing purposes. The truest reaction is between tin 2 and permanganate. Sometimes that's hard to pull out, so I just want to make sure you're good with that. Okay, ignore the data right now. Let's just go straight for balancing our equation. So, first half reaction is what? Tin 2. Tin what? Okay, so our options really are either tin solid or tin 4. So you guys are telling me you go to the highest oxidation state, tin 4. Let's verify we're good with that by looking at the opposite reaction, because you remember it's always redox, right? Reduction and oxidation. You have to have one of each. So what's happening here? Add what? 2 electrons, so that's tin 4 going back down to tin 2. So this one is oxidized or reduced? So it's lost electrons, right? So I'm just going to put oil over here just to remind myself that I do have one oxidation, one reduction. So then potassium permanganate, you guys predict that half reaction down there. Okay, because it's in acid, right? So you're going from permanganate to manganese 2 plus. It's in acid. If it were in base, what would it make instead? Manganese dioxide, right? It's the other one. Look on your little cheat sheet. All right, so we are making this. You're adding 4 waters, adding 8 H pluses, and 5 electrons. And that for sure is the opposite, right? So we have reduction occurring, so we're good on both of those. And what's my next step here? Multiply by what? Top one by 5, bottom one by 2. All right, here we go. go ahead and pull your stuff down together. I'm going to focus as I write this time. I can always follow along. All right, so once you get your balanced chemical equation, what is the ratio between the two reactants of choice here? 5 to 2, right? 2 permanganates react with 5, 10, 2 pluses. The acid is just there to balance. All right, so going back up here, first of all, we have 0.3 grams of the ore. It was titrated with 8.08 milliliters of 0.05 mole of potassium permanganate. Okay, so far, who is the known? Potassium permanganate, right? You always start with your known. All right, so we know we're going to utilize these two pieces of information together. How many grams of the tin were present in the original sample, and then what was the percentage of tin in the ore? All right, so in A or B, which of those options will I be using this? I heard, Cass, what did you say? I said B2, because that's the original sample, right? That's the original ore. I heard a lot of people say A. But in the original ore, that mass that you had was 0.3 grams. You do not need that right now because, as you probably can maybe read between the lines, it's kind of telling you that not all of the ore is tin. It's like rock and other stuff, and then there's tin in it. So we won't use that number until the very end. But the very first part we have to do is just to get to grams of tin. So let's work backwards. If I got to grams of tin, what did I get to before that? Moles of tin. Okay, so how did I get to moles of tin? Probably the mole ratio between what and what? Okay, the potassium permanganate and tin, which is the 5 to 2 thing down here. Well, how did I get 2 moles of potassium permanganate? Okay, so I know, so we're just permanganate, maybe not potassium permanganate, but yes, the molarity in the volume. Okay, so you can sometimes think from the end back to the beginning to make sure you can follow through, but regardless, we have to start off with these 2 data points, right? So I'm going to try to squeeze my work right here. It may not be pretty, but here we go. 8.08. Oh, you guys want to do millimoles or moles? Millimoles it is. You have found a new love for millimoles. Okay. So 8.08 milliliters. 1 milliliter on bottom, 0.0500 millimoles of potassium permanganate. Okay, what do you guys want to do from here? Okay, we want to go internal. Sometimes that's super important, and I like to make sure you guys are recognizing potassium permanganate and permanganate are a one-to-one in itself, but recognizing it and writing down in stoichiometry is sometimes important. Especially if you're going to molar mass in the end and you don't include the whole compound, that's where you get in trouble. So this is a one-to-one internal mole ratio with permanganate ion. Okay, now I'm in permanganate ion. Where do I want to go next? Moles of tin ion, right? So 2 millimoles of permanganate ion for every 5 millimoles of tin 2 plus. And specifically, because that's for tin, not tin 2 plus, so we should actually show the relationship between tin and tin 2 plus, which is what? 1-to-1. I know it's ridiculous because it's a 1-to-1, but I'm going to show that anyhow. So in 1 millimole of tin 2, and that's kind of regarding back to this relationship here, there's 1 millimole of tin. Sorry, it's getting squished up here. And then I need to go one more step. Milligrams, right? I can go from millimoles to milligrams, or I can just go straight to grams, depending on how you want to go with that. Let's go to grams. So you guys take the millimoles to milligrams to grams. Just need some space real fast. Oops, I lost my electrons.
Or I'll go to millimoles first.
Right, calculate, guys, calculate. Is anybody trying to mentally calculate? You can try. What's 8 times 5? 40 divided by 2. 20 times 100. 20 times 100. 20 times 100? 2,000, so it's technically more than that. Okay, what's 2,000 divided by 1,000? 2. Okay, what's 2 times 0.05? 0.01, right? I'm sorry, 0.1, not 0.01. 0.1, the answer should be 0.119887. All right, so we could technically do that if we had to on multiple choice. You wouldn't have to do that much on multiple choice. But that's a pretty good guesstimation there. Okay, so I am not rounding just yet, I'm going to show you the full answer. That's the grams of tin that was extracted from the tin ore. So technically, how many sig figs should I have? 3, so it should be rounding to what if this were my final? 120 grams of tin. Okay, so that's like the answer you would circle and like this is the answer. But I'm going to utilize this to not have any rounding error for the next part. So for B, what was the percentage of tin in the ore? How would you find the percentage of tin in ore? That over 0.03, right? 0.300 grams times 100, none. So B is very easy once you get A. I'm going to write B in a different color right here. So 0.120 grams of tin over you guys can guesstimate this too. 10 total. So what's 0.12 over 0.3? Well, it's a little bigger than half, right? I mean, it's a little less than half. So is it about 40%? If you had to guesstimate, that'd be about 40. So it's 39.96. So we'd round that to 40. So 40.0%. Or it's close to 50% if you really round. All right. This one was, of course, more challenging. Take a second to absorb, and then we'll have one more for you. Okay. It's on your paper. It's number 3. It's number 3. I have to go back and work and erase. She's focusing herself. She's saying the question out loud. This one tells you all the answers in it. Peroxide sulfate. Check yourself before we go. Which one? When you take your 2 times 3 plus is a 6 plus, and then 12 plus, so I mean decrease the 12 plus down to 6 plus by adding 6 electrons. Yeah. It's not really important for this question. I'd have to go back and add in spectator ions. So I'd have to have 6 potassiums. So this is the NIE, right? So this potassium ions and the nitrate ions would be gone. They would be here though in equal quantities on left and right. So like 6 potassium and 1 chromium. 3 nitrates on each side. No, 6 nitrates on each side. So it would be spectator though, all the way. They'd be gone at the end. All right, so give me a thumbs up if I can move on. All right, so what was difficult about this one? Was it the addition of this 2 in the front right here first? Did you guys recognize that? For the sulfurs and sulfurs, you had to do that, and that naturally already balanced the oxygen count. So it's 2 sulfurs, 8 oxygens, and then overall this is a 4 negative charge, this is a 2 negative charge, so you've got 2 electrons here to get down to the lower -4. And then we've done this reaction like 3 times today, but we flip it because of the powerful oxidizing agent, so therefore it was then reduced, or no, it was oxidized, my bad. So then the chromates balance first, and then your 7 waters, and your 14 H pluses, and your 6 electrons. Sum those up. What's your ratio between the 2 reactants? 2 to 3, okay? So starting back up here, blah, 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 blah. What mass of potassium peroxidized sulfate is required to oxidize 100 milliliters of 0.2 molar chromium 3 nitrate? Okay, so we're using the full quantity, like the full identity, which is why we have to recognize the ion internal ratio back to itself. So where do you guys want to start? With potassium peroxidized sulfate? Yes or no? You can. That's the question, right? You not start with that. Right. So I have to start with. Yeah. You're like, yeah. Whatever you say. And then we'll start with that one. No. So think about it. We're talking with 100 mils of 0.2 molar, a 0.2 molar potassium or chromium 3 nitrate. So millimoles are what? Let me go back to how I did it. I'm going to get a moles just for a change. 0.00 liters. 0.100 liters of chromium 3 nitrate. Okay. What do I multiply by? 0.020 moles of chromium 3 nitrate in a 1 liter solution, so that's its molarity. So I've gone to moles of chromium 3 nitrate. And then what? Internal mole ratio to get to what? To get to chromium 3 plus. So for every 1 mole of chromium 3 nitrate, there is 1 mole of chromium 3 plus. And now we're talking business because there's our chromium 3 plus I can now work with. So I'm in chromium 3 plus, and then what? 2 moles of chromium 3 plus for every 3 moles per oxy disulfate. Okay, so are you guys following me from here to the chromium internal? And then just this is a mole ratio from my ECE I got ahead. Now I'm in peroxydisulfate. Where am I going? Potassium peroxydisulfate, right? So inside of potassium peroxydisulfate, how many peroxydisulfates are there? All right, so 1 mole of peroxydisulfate for every 1 mole of potassium. I always want to write permanganate. Potassium peroxydisulfate. Okay. Also, just ignore that. I keep wanting to write charges too. Okay. Now we're in moles of potassium peroxydisulfate. Now where do I want to go? 2 grams. I got you. Molar mass. 270.12. 1 mole of potassium peroxydisulfate. 270.1 grams. All right. Before you start plugging, we're gonna start mentally calculating. I like to try. Okay. So. Where do you guys want to go first? Okay, let's do this. Let's do what's 0.1 times 270? 27. Right, that's decimal back one. So what's 27? What's 2% of 27? Okay, hold on. What's 1% of 27? 0.27, because 27 is 1% of that will be back. So that's 0.27, but I'm actually taking 2%, not 1%. So it's technically be what? 0.54. So 0.54 times 3 divided by 2. Hold on. What's 0.54 times 3? About 1.5. 1.5 divided by 2. About 0.75. 0.810. It's falling and it's in the ballpark, right? We're good. So this answer is 0.810 grams. We'll keep practicing now that I got some hard math on the board here. All right. That's our grams of potassium peroxydisulfate. This one? Yeah, we did at the beginning. 0.1 times 270 is 27, but 1% of 27 is 0.27, but that's actually 2%, so it's 0.54. 0.54 times 3 is about 1.5, about 2 is about 70, or 0.75. So, okay. All right. Here's what I want. Hold on one second. Here's what I want from you. You can attempt 1 through 5, but I specifically want you to be able to accomplish 4 and 5. 5 is the best one. Like 4 and 5. Do you guys see that on your problem set? 4 and 5. Okay, so you have 10 reaction predictions and 2 stoichiometry problems. Because I think the harder part is probably the reaction prediction, because you guys can stoich it up. All right, if you need to ask me questions in lab or talk to each other in lab, now's the time. Please come and see me if you have lab questions.